Hi, welcome to Norton Chemistry. Today we're going to be going through AS level chemistry paper, breadth paper from 2016. So it's a 1 hour 30-minute paper. They're slightly shorter than the A level papers. So let's get started. Which row shows the atomic structure of 37 Cl-? So the mass number of this isotope is 37. The isotopic mass is 37. So if we want to find the number of protons, we simply subtract 37. Well, we know the number of protons is going to be 17 because if you look at the periodic table, you look for the atomic number. The atomic number of chlorine is 17. So it's either A or B, so it can't be C or D because they're not 17 for the number of protons. Then we can look at the number of neutrons, which we'd calculate by subtracting the relative isotopic mass, which is 37, from the atomic number, which is 17, and that gives us 20. So therefore it must be B. But let's just double check because we have a minus charge on our chlorine ion. So that means that we've got an extra electron from what you would normally have, and the atomic number is 17, so that's the number of electrons in the atom. So if you add 1 onto that, you get 18, which is correct. So it must be answer B. Question 2. What is the formula of ammonium sulfide? So we know that ammonia has the formula NH4+, and the sulfide ion, if you look at sulfur on the periodic table, it's in the same group as oxygen, and oxygen has a 2- charge, so it's going to be S2-. And then that means that if we use Avogadro's rule, we need 2 of these ions and 1 of this ion to balance out the charges in the compound. So that gives us answer C. And then question 3. Calcium nitrate, CaNO3 decomposes when heated, as shown below. So we've got CaNO3 being decomposed to calcium oxide, NO2, 2NO2, and half a mole of oxygen. A student decomposes 0.005 moles of CaNO3 and collects the gas that is produced. So they're doing gas collection and they are decomposing that many moles. Calculate the volume of gas that the student should expect to collect, measured at room temperature and pressure. So if we look at what gases we're forming, so CaO is solid, so that's not a gas, so we don't need to count that. NO2 is a gas, and we've got 2 moles of that, so we need to count that. And we've got half a mole of O2. So we need to find out, and we have 1 mole of CaNO3 at the start. So then we're forming 2.5 moles of gas for every 1 mole of our solid CaNO3. So then we need to times 0.005 mole by 2.5 to get the moles of gas which we're forming, which gives us, if you put it into the calculator, 0.0125 moles, which we can use then to find the volume of gas at room temperature and pressure. That means we can use the gas constant, which is 24 dm cubed, or 24,000 centimeters cubed. So volume is equal to the gas constant times the number of moles. So volume is equal to 24,000 times 0.025 moles, which gives us an answer of 300 centimeters cubed, which, if we look at our answers, is answer D. Question 4. Which equation is not a neutralization reaction? So the key word there is not, and also neutralization. So let's have a look at A. So we've got Ca, which is a metal, reacting with HCl, which is an acid, forming a salt, and H2 gas. So straight away that looks like it's not neutralization to me, because a metal is reacting with acid, and a neutralization reaction is a reaction in which an acid reacts with a base. So it can't be, I think that is the answer, but let's just check. So H plus plus OH minus goes to H2O, that's obviously neutralization. A carbonate plus an acid, so a base plus an acid, so that's, and we're forming water, that's definitely neutralization. And then a D, a NH3, a base, reacting with HCl and acid, forming a salt, that's neutralization, so it must be A. 5. What is the oxidation number of nitrogen MgNO32? So we want to set this out like this and identify first the oxidation number of oxygen, which is generally always -2 unless it's in a compound with fluorine. And then we've got 3 oxygen atoms here and 6 overall if you times it by 2 for the brackets. So 6 times -2 is -12 overall. And then Mg is in group 2 in the periodic table. So that means that we need to give it a +2 oxidation state. So if we add 2 to our -12 for oxygen, that leaves us with -10. And that's what we need to get rid of with our 2 nitrogen atoms, which means our nitrogen atoms, which we're trying to find, need to be +5 to give us overall 0 oxidation state, because it's a neutral compound. So that is answer C. Question 6. How many orbitals are occupied in a silicon atom? Well, if you have a look at the periodic table, you can see that silicon is in group 4. And so I always find it easiest to draw out electrons in a box to represent the orbitals visually. So we've got our 1s orbital, our 2s orbital, and our 2p orbitals. And then we have 3s. I'm referring to the periodic table while doing this. And then 3p. And you can draw them like this. So remember that orbitals, the lowest energy orbitals fill first, and orbitals fill singly, then they pair. So this is all full. And then 3p is where we have empty, or well, not empty orbitals. Yeah, empty orbitals. So we have our 2 electrons in the 3p orbitals, and then all the other orbitals are occupied. So that's 1, 2, 3, 4, 5, 6 orbitals which are occupied, but then we have obviously 7 and 8. So that gives us answer C. Notice it says, I almost made the mistake there. Notice it says occupied, not fully occupied, so it can include partially occupied orbitals. Question 7. A dot and cross diagram for nitrogen trichloride, NCl3, is shown below. Which row shows the correct shape and bond angle in a molecule of NCl3? So, if we have a look at our diagram, we can see that we have a lone pair here, lone pair, because it's not in any, and this is our central nitrogen atom, and then we have 1, 2, 3 bonded pairs. So we're not worried about these lone pairs because these lone pairs aren't on our central atom. And then, so it's just remembering what the shape and bond angle is for 3 bonded regions or bonded pairs and 1 lone pair. So that is pyramidal, and it's 107 degrees, because it's a reduced bond angle due to this lone pair, because lone pairs repel more strongly than bonded pairs. So if we had 3 bonded pairs and 0 lone pairs, it would be trigonal planar 120 degrees. But instead it's answer B, pyramidal 107 degrees. Really important to nail down those key concepts ahead of A-level exams. What is the shape around the carbon atoms in graphene? So this is going back to GCSE. So you need to think about the structure of graphene. So in graphene, each carbon atom is bonded to 3 other carbon atoms. So, and it has 1 delocalized electron per carbon atom. So that gives us 3 bonded pairs and 0 lone pairs. So that means that is, as we said earlier, D, trigonal planar, which would have a 120 degree bond angle. Question 9. Electron configurations for atoms of different elements are shown below. Which electron configuration represents the element with the largest first ionization energy? So, if we have a look at our electron configurations, 1s2, 2s2, well, that's beryllium. And then we've got B, which is 1s2, 2s2, 2p4. So 1s orbital is full, our 2s orbital is full, and our 2p orbital has 4 electrons in it, that's oxygen. C, 1s2, 2s2, 2p6, that's a full 2p subshell, so that's Ne, neon. And then 1s2, 2s2, 2p6, 3s2. Well, that is magnesium. So ionization energies, they across periods, so you have to consider across period, down group. So across periods they increase, and down groups they decrease. So that means that it must be oxygen, because no, sorry, it must be neon, because that's the so you got beryllium, oxygen, and neon are all in period 2. So there's not going to be any group difference between them. We can immediately remove Mg, magnesium, because it's in the lower period. And then it's in period 3. And then, so we're looking at Be, O, and Ne. And Ne is the furthest to the right in that period. It's all the way to the right. So across the period, our ionization energy is going to increase like this. So apart from the anomalies for the partial filling and pairing. So then that gives us answer C. Question 10. Successive ionization energies of 4 elements in period 3 are shown below. Which letter could represent magnesium? So if we have a look at our ionization energies, we need to look for where there's any large gaps. And just by eyeballing A, I can't see any really large standout gaps. So it's probably not going to be magnesium, because that's a group 2 element. So we'd expect a large increase from the 2nd to 3rd ionization energy as we enter the lower energy subshell. So the electrons that we're removing are closer to the nucleus, so there's a greater nuclear attraction and more energy is required to remove the electrons, 1 mole of electrons. Remember our definition, which is the energy required to remove 1 mole of electrons from 1 mole of gaseous atoms from 1 mole of gaseous 1+ ions for first ionization energy. So I can see a large increase for 2nd to 3rd for B, and no other really large increases or out of the trend increases. Then there's a quite a large increase here, but potentially might not be significant. But you wouldn't expect that for Mg. And then a large increase from third to fourth. Well, that wouldn't be expected for Mg because that would just be going from that wouldn't be going to a new subshell, so a new shell. So we'll go with answer B. 11. A student adds aqueous sodium carbonate to one test tube and aqueous silver nitrate to a second test tube. The student adds dilute sulfuric acid to each test tube. Which row has the correct observations? So, aqueous sodium carbonate is going to provide carbonate ions, CO3 2-, and silver nitrate we're going to get Ag+ ions which react with halides. So, and the student adds dilute sulfuric acid. So when we add an acid to a carbonate, we expect CO2 to form, which is a gas, so it must be C or D. It can't be A or B because there's no change, there's no effervescence, even in the presence of a carbonate and an acid. So then we need to look at our silver nitrate, and in the presence of having removed Ag+ would actually react with the carbonate ions, forming a precipitate. So that would give us answer D. That's why when you're doing qualitative testing, you first do carbonate, so adding acid, then you do sulfate, then you do halide, because when you add AgNO3 to any of if you have SO4 or carbonate ions present, you're going to form a precipitate, which could lead to confusing results. Question 12. The enthalpy change of formation of butane can be calculated using the enthalpy changes of combustion, delta CH, shown below. So we're given the enthalpy changes of combustion, and they're asking us to calculate the enthalpy change of formation of C4H10. So we want to draw a Hess cycle using the combustion values. And when we're drawing a combustion enthalpy cycle, we need to do the arrows downwards. When we're given formation values, we need to draw the arrows upwards. And this equation here is actually the equation for the formation, because remember the definition. Enthalpy change of formation is the enthalpy change when 1 mole of a compound is formed from its constituent elements, obviously standard states, etc. So then we need to input our values. That's 4 lots of -394 for our carbon, plus 5 lots of our -286 for our hydrogen, and then we just have 1 -2877 for our butane. So if we do that, those first initial calculations, that's -1576 plus 5 lots of -286, which is -1430, which gives us -3006, and then we need to we're going with this arrow and we're going against this arrow, so then that gives us -3006 plus 2877, which is, I'm estimating it's answer B. Yeah, -129 kilojoules per mole. So that's answer B. So when you're drawing your Hess cycles, the main thing to remember If you're given combustion values, then arrows down. If you're given formation values in this table, then if you're given combustion values in the table, then downward arrows. And then, so yeah, I didn't really explain properly, but this is negative. We need to make it positive because we're going against this arrow. Question 13. The skeletal formula of 4 alcohols E, F, G and H is shown below. Which pair of alcohols are structural isomers of each other? So structural isomers, let's define that first. That is same molecular formula, different structural formula. So if we have a look at our alcohols, we have an alcohol here with 1, 2, 3, 4, 5 carbons. We have one here, 1, 2, 3, 4, 5 carbons. Then we have 1, 2, 3, 4, 5, 6. So that's looking, well, that's obviously not going to have the same molecular formula as the others. And 1, 2, 3, 4, 5. But we have this double bond which isn't present in any of the others. So that's going to reduce our number of hydrogens below the molecular formula of the others. So that means that it must be E and G, which if we look at our answers, gives us answer B. Question 14. What is the name of the compound shown below? Well, it is a dichloro compound straight away. We've got 2 chlorine groups. And then it's easier if we just draw it out and then we can number it. So we want to go for the lowest numbers possible. We want to identify the longest chain first. So that's 1, 2, 3, 4, which means it must have a butane base. That's the longest chain, is 4, so that's butane. And then we have a methyl group at position 2. But we also have these dichloro groups. So we need to put the chlorine groups first because that is in alphabetical order. And so just in case you aren't aware, if we were to go the other way, that wouldn't be ideal because then we would have 2, 3 dichloro, 3 methyl, which would be higher numbers than what the correct answer is, which is 2, 3 dichloro. I've lost space, but 2 methyl, because that's lower numbers. So you always go for lower numbers, and it's always in alphabetical order for this the extra groups. So that is 2, 3 dichloro, 2 methyl butane, which is answer C. Question 15. Which compound has non-polar molecules? So we've got EZ stereoisomerism, which we need to think about. So let's draw out. It's easier to just go ahead and just draw. We've got lots of space here to play with. So let's go ahead and draw out our molecules. So we've got A, which is E. So that's the groups are on opposite planes of the double bond. So that's 1, 2 dichloro. Chlorine groups are going to be higher priority. Sorry, on opposite sides. And then B, we got E2, 3. Sorry, that's wrong, incorrectly drawn. 1, 2 dichloro, butene. Okay, so that's C2HCl. 1, 2 dichloro, butene. Yeah, and H. Yeah. And then B is 2, 3 dichloro, so it's what I just drew. E, so it's the highest priority groups on opposite sides. And then CH3 and CH3. C is Z, 2, 3 dichlorobutene, so that's on the highest priority groups on the same side. And then this is a 1,4-dichlorobutene. So that would be so the highest priority group's on the same side. So if we have a look at these molecules, we need to think about which ones dipoles don't oppose. Because if dipoles oppose, they cancel each other out. So these dipoles oppose. This dipole here opposes this because they're attached to the same here. Then they oppose, so it can't be that one. These won't oppose because they're on opposite sides of the bond, so they're not going to cancel each other out. And then these two will oppose, so they'll cancel out, it won't be polar. And then these two will oppose as well because they line up with each other, so they'll cancel each other out. So that gives us answer B. Question 16. The displayed formula for a hydrocarbon is shown below. How many sigma and pi bonds are present in a molecule of this hydrocarbon? So, remembering that sigma bonds are single carbon-carbon bonds, and they are also carbon-hydrogen bonds. So students often forget that sigma bonds are carbon-hydrogen bonds. So if we just go ahead first and count all of our sigma bonds, so we've got 1 here, 2 here, as in I've counted 2. Then in this double bond, we've got 1 sigma bond and 1 pi bond. So we'll just start with our sigma bonds. So that's 3 sigma bonds, 4 sigma bonds, 5 sigma bonds, 6 sigma bonds, 7 sigma bonds, 8 sigma bonds, 9, 10, 11, 12. So then we know straight away it must be answer D because all of these have incorrect numbers. But let's just check our number of pi bonds. So in each double bond we have 1 pi bond. So that's 1, 2, and that's correct. So that gives us answer D. Question 17. Chlorine reacts with 1-chloropropane in the presence of ultraviolet radiation via a radical substitution mechanism. Which equation shows a propagation step in the mechanism for this reaction? So have a look at those equations. What do you think is propagation? So propagation is when we usually have 2 propagation reactions, and a radical reacts with a compound forming a radical and a non-radical compound. So straight away, A is initiation because we have this chlorine molecule, this diatomic molecule, forming 2 radicals. So in propagation, we only form 1 radical, so it can't be that. Then have a look at the next one. That's clearly termination because we have 2 radicals reacting together to form a stable compound. So it's not B. Then it could be C because we have a radical reacting with a compound to form a compound and a radical. However, this isn't how radicals react. This is how it should be like D. It should form a radical carbon compound and HCl, because hydrogen radicals don't form, they can't exist, because hydrogens don't have unpaired. When you have a hydrogen atom, it only has 1 electron. It's always has an unpaired electron. So a hydrogen radical can't really be formed because hydrogen on its own would form a diatomic compound molecule. So therefore it must be answer D. So anytime you see hydrogen radicals, you know it's wrong. Question 18. Which alcohol can be oxidized by potassium dichromate? and H2SO4 to form a ketone. So we know that when we oxidize alcohols, we can only form ketones from secondary alcohols. So let's go ahead and identify what these alcohols are. So A is a primary alcohol because the carbon that it's attached to only has one alkyl group attached. Then we've got B, which is a secondary alcohol, so it could be B because it has the carbon that the alcohol group is attached to has two alcohol groups. Using that same reasoning, 1, 2, 3, that's a tertiary alcohol, and then D is a primary alcohol, so it can't be C, it can't be D, it can't be A, it must be B. Question 19. A reaction sequence is shown below. So we've got butyrene reacting with HBr, forming 2-bromobutane. And then in step 2, that 2-bromobutane goes on to react with sodium hydroxide by nucleophilic substitution, forming butan-2-ol and sodium bromide. So at the first step will be electrophilic addition, because we have an alkene which always reacts by addition reactions, reacting with HBr, which has a polar bond. Not that it really matters because the alkene bond can polarize it. So the electrons attack the delta positive hydrogen, form the electrophile. So electrophilic addition. So then it can't be C and it can't be D. And then step 2, we have a nucleophilic substitution, because our NaOH is going to form OH minus nucleophiles, which are going to attack the delta positive carbon on the carbon bromine bond, which will remove that bromine atom, and that will go and react with the Na plus arm which is formed, and that will replace it with the OH group by nucleophilic substitution. Question 20. When heated with NaOH, 1 iodobutane is hydrolyzed at a much faster rate than 1 chlorobutane. Which statement explains the different rates? So the carbon-iodine bond enthalpy is greater than the carbon-chlorine bond enthalpy. Well, that can't be correct, because if the bond enthalpy is greater, it's going to take more energy to overcome, which means it will occur at a slower rate. The CI bond is less polar than the CCl bond. No, that's not a valid reason. The CI bond has a carbon atom with a greater delta positive charge than the CCl bond. No, that's not a valid reason. So it must be answer D. And if you have a look, the CI bond requires less energy to break than the CCl bond. Yes, that's correct. So as you go down the group, the strength of the carbon hydrogen bonds decreases, so the rate of hydrolysis increases. So then it must be answer D. And that's all the multiple choice questions done. I would usually recommend doing the multiple choice questions after you go through the long answer questions, but for the video I just started with the multiple choice questions. It depends what you prefer, so try it out in your exams at school and see how it goes. But multiple choice questions you can often spend too much time on, and that can cause you to lose easier marks elsewhere, because multiple choice questions aren't really that easy for the marks. You can see I've obviously been explaining it, but it's taken me nearly 35 minutes to do them while explaining them, and there was only 20 marks available. But they are still really important questions, and they account for 30 marks for A level, so you need to get good at them. But yeah, if you leave them till the last minute, then you can guess and make it a bit easier for yourself. 21A. A 20p coin contains copper and nickel. Copper and nickel each exist as a mixture of isotopes. State the similarities and differences between the atomic structures of isotopes of the same element. So, isotopes are they have the same number of protons and electrons as each other, So for example, every isotope of hydrogen will have one proton and one electron, but the difference is that they have different number of neutrons. So for example, deuterium, which is an isotope of hydrogen, it's called heavy hydrogen, has one neutron, which hydrogen 1 doesn't have. The copper used to make a batch of coins is analysed by mass spec. The mass spec is shown below. Calculate the relative atomic mass of the copper used to make the coins. Give your answer to 2 decimal places. So just make a note of that. And then we use the formula AR equals the sum of the abundances multiplied by relative isotopic masses, or MZ. Relative isotopic mass divided by the sum of the abundances. So I have enough room for myself there, but I needed to write it out for you. And then, so that means that we need to do 69.17 multiplied by 63 plus 30.83 times 65. So that's our sum of the abundances multiplied by the relative isotopic masses divided by the sum of the abundances. So that's going to be 69.17 plus 30.83. It's usually 100, but it's always worth double checking because they sometimes try and catch you out, but it is 100 this time. So divide it by 100, and then that gives us 69.17 times 63. Put it in the calculator. Gives us 63.6166, which is, to 2 decimal places, 63.62. One coin has a mass of 5 grams and contains 84% copper by mass. Calculate the number of copper atoms in one coin. Give your answer in standard form to 3 sig fig. So 3 sig fig and standard form. So for 5 grams of a coin, 84% of that is copper. So that is 4.2 grams. So our moles of copper in one coin is 4.2 grams divided by the MR of copper, which is 63.5 grams per mole, which is 0.0661 moles. Then to find the number of copper atoms in one coin, we need to multiply that by the number of moles by Avogadro's constant, which is in the data sheet, and it's 6.02 times 10 to the 23. You'll sometimes see it represented as Na. And that gives us a value of, making sure to carry down our value from our calculator, not round it mid-calculation, 3.98 times 10 to the 22. We're giving it to 3 sig fig, so there would be a 1 there, but we're giving it to 3 sig fig, so it's 3.98 times 10 to the 22. And then part C, nickel 2 nitrate, NiNO32, can be prepared by reacting nickel 2 oxide, which is going to have the formula NiO because oxygen has a +2 oxidation state, with dilute nitric acid. So these italics show the oxidation state of the nickel. So they want us to write the equation for the reaction with dilute nitric acid of nickel 2 oxide. So that's NiO plus HNO3 goes to NiNO32 and H2O, which is then we need to balance it. So we've got 2 NO3 on this side, so then we need to balance that, and that gives us perfectly balanced equation. They haven't asked for state symbols, but it's always good to give them. So that's going to be a solid. It's going to be aqueous. It's going to be aqueous, and that's going to be a liquid. NiNO32 contains the NO3- ion, which they often like to test. The nitrogen atom bonds to the oxygen atoms with a single covalent bond, a double covalent bond, and a dative covalent bond. So you can see the dative bond here, the single bond here, and the double bond here, as shown below. Draw the dot and cross diagram for the NO3- ion. So they've literally told you how to do it. All you have to do is put it into the correct format, showing outer shell electrons only. Use a different symbol for the extra electron. So our extra electron is the one that gives this oxygen a negative charge. So when we're drawing it, we draw our nitrogen in the middle. Hopefully you're better at drawing than me. And then our oxygen, 3 oxygens, and don't forget your overall negative charge. And then, so nitrogen, you can see from the periodic table, has 5 electrons because it's in group 5 outer shell electrons because it's in group 5. So first we'll do our double bonds. We know that there needs to be 4 electrons in there. Then our single bond needs to be 1 electron from each atom, and then our dative bond will both electrons be from the nitrogen, so we'll represent the nitrogen electrons with dots, and then our oxygen electrons. So each oxygen atom, as it's in group 6, there's 6 outer shell electrons, but then we don't forget this oxygen here is negative, so we'll draw a triangle for our extra electron, which is gained, like for example, from hydrogen, which forms H+ in HNO3, and then this is going to have 6 oxygen electrons, and this will have 4 on the outside because there's 2 in here, so that gives 6 overall. For oxygen electrons, 8 overall, completing the octet. So we've got a question about salts. So a hydrated salt, compound A, is analysed and has the following percentage composition by mass. Calculate the formula of compound A, showing clearly the waters of crystallization. So we want to first calculate our empirical formula. So we'll write out our table. I always like to use a table, just because that was the method I was taught, and it makes it a bit easier to lay it out and not miss any rounding or numbers. So mass, moles, simplest. You can add a column for adjusted, but I would just like to go with 4 columns, and then empirical. And then our masses are 19.51 for CR, 39.96 for Cl, 4.51 for H, and 36.02 for oxygen. And then we need to divide by our MRs, our ARs to get our moles of each. So the AR of chromium is 52. The AR of chlorine is 35.5, and then hydrogen and oxygen. So 19.51 divided by 52 gives us 0.375 with lots of extra numbers, so we'll save to our calculator using the recall function as A. And then 39.96 divided by 35.5 gives us 1.12 with lots of extra numbers, so we'll save that as B in our calculator. 4.51 divided by 1, well that's just 4.51, and then 36.02 divided by 16 should be hang on, 2.25 with lots of extra digits, so save that as D. And then we want to find our simplest ratio, so we do that by dividing by the smallest number of moles, which is 0.375 from CR. So then we'll go ahead and divide them all, so that's 1 for CR obviously, and then for Cl that gives us 3 with lots of zeros, and then for H we get, for hydrogen we get 12, and then for oxygen we get, bear with me, we get 6. And then we can write our empirical formula, which is CrCl3 H12O6. So then we can use that to find our number of our waters of crystallization. So our salt is just going to be CrCl3, and then we represent it with a dot, and then use your, so when you're, and then so we know that we can only have 6 water molecules, because that gives us the correct number in the empirical formula. Part B. A student carries out the experiment to determine the amount of waters of crystallization in the formula of another hydrated salt. The student intends to remove the water by heating the hydrated salt. A diagram of the apparatus used by the student is shown below. So they're using a crucible and a pipe clay triangle to heat the hydrated salt, removing the waters of crystallization. The student adds the hydrated salt to the crucible and weighs the crucible and contents. So the first thing they do is weigh the crucible and the solid. And then the student heats the crucible and contents and allows them to cool, and they reweigh the crucible and the residue. So they're asking us what the maximum error on each mass measurement using the balance is. They're asking us to calculate the percentage error using that maximum error. So the formula for percentage error is the uncertainty in each measurement times the number of measurements over the smallest measurement. So then we'll do that. They're doing 2 measurements. You can see 1, 2. So that's 2 times 0.005. So that's our uncertainty, is plus minus value here. And then we're dividing it by the measurement, which is when you subtract 16.84 from 16.26. Because that's a difference. That's what you need to calculate. That's what they're measuring, in fact. That's what we're going to use for our uncertainty, and that is 0.58. So then we need to put that on our calculator, and that gives us, when we multiply it by 100, don't forget to do that, that gives us 1.72%. So that can often be tricky, but if you practice it in all the different contexts, so it often comes up in titrations as well, you can usually know how to do it. And also when you're measuring temperature, for say for example when you're measuring enthalpy changes in practice. Suggest one modification that the student can make to their method to reduce the percentage error in the mass of water removed. So they've heated, and then they haven't checked that they've removed all the water. So that means that there could still be some water left. So that means they need to reduce the percentage error. They need to heat to a constant mass. III. The student is not sure that all the water crystallization has been removed. Sorry. Actually, yeah. So no, sorry, that would be incorrect. So you would to decrease the percentage error, you would need to either increase this this value. So by using a balance to like how many was it? So this is the 2 dp. So we want to balance the 3 dp to reduce that uncertainty. To make it more precise. And then you could increase your masses. So then you get a larger measurement, because it's just a ratio really. So if you increase that mass on the bottom, then you decrease the percentage of uncertainty. and then the answer that I said before, that's the correct answer for this, because they're not sure that it's all been removed. So they need to modify it to check that all of it has been removed. Part C, a student prepares a solution of sodium sulfate Na2SO4 by adding 6.25 times 10 to the minus 2 mole per dm cube sulfuric acid from a burette to 25 centimeters cubed of 0.124 mole per dm cubed NaOH in a conical flask. So our ratio of NaOH to H2SO4 is 2:1. Calculate the minimum volume of the H2SO4 that the student would need to completely react with the NaOH present. So we need to calculate our moles of NaOH, which is our concentration times our volume. (25/1000) times by 0.124 mole per dm cubed. Which is 3. Always put units, make it easier for yourself. 3.1 times 10 to the minus 3 moles. And then we need to find the moles of H2SO4, which is the moles of NaOH divided by 2. So that's divided by 2, which is 1.55 times 10 to the minus 3 moles. Then using our moles of H2SO4, we need to find the volume. And we've got the concentration, so the volume is the moles over the concentration, because we've rearranged this equation to give us the volume, which is 1.55 times 10 to the minus 3 divided by 6.25 times 10 to the minus 2 mole per dm cube, which is which gives us a volume of a volume of 0.0248 dm cubed, which when you multiply by 1000, because they want it in centimeters cubed, you get 24.8 centimeters cubed. Question D. Salts can be prepared in redox reactions of metals with acid. A student prepares a solution of aluminium sulfate by reacting aluminium with dilute sulfuric acid. So 2 moles of aluminium reacts with 3 moles of H2SO4. Using oxidation numbers, show which element has been oxidized and which has been reduced in this reaction. State the changes in oxidation numbers, including all signs. So they want us to work out what has been oxidized and what has been reduced. So let's go ahead and write out the equation, and then we can write our oxidation numbers below and work it out. So Al, H, S and O. So Al is going to be 0 because it's just an element on its own. Then -2 for oxygen, because it's always -2 unless it's in a compound with fluorine. And then +1 for hydrogen, because it's usually +1. So -2 times 4 is -8. If we add 2 onto that for the hydrogens, that's -6. So that means the oxidation number of our sulfur is +6. And then we need to find our oxidation numbers in Al2SO43. So -2 again for oxygen, times that by 4, that's -8, times that by 3, that's -24. Then our aluminium is in group 3, so it's going to have a +3 oxidation state. So when we add 6, because there's 2 aluminium atoms, that gives us -18. And then that's what we need to get to 0 using just our sulfur. We've got 3 sulfur atoms, so we need to divide -18 by 3. That gives us -6, so +6 for the sulfurs, because you need to add it on to make it up to 0 because it's a neutral compound. And then H in H2 is obviously just going to be 0 because it's a element on its own. And then what's been oxidized and what's been reduced? Well, our aluminium has gone from 0 to +3, so that is oxidation. From 0 to +3. And element reduced is going to be hydrogen, because that's gone from +1 to 0, so that's decreased. 23AI. This question is about properties of halogens and halide ions. Bromine can be extracted by bubbling chlorine gas through concentrated solutions containing bromide ions. So bromide ions are Br-. So write the electronic configuration of a bromide ion in terms of subshells. So if we refer to our periodic table, we can see that bromine is the bromine atom is in the 4p subshell. So it's going to be quite a long one, but we can get there. So it's going to be 4p6, because when you add an extra electron, because they're asking for the bromide ion, so it's going to be end with 4p6, because when it becomes a 1- ion, it gains an extra electron. So it's 1s2, 2s2, 2p6, 3s2, 3p6. Don't forget 4s fills first, so 4s2, 3d10, which is going to be 4, and then 4p6. Write an ionic equation for this reaction and state why the reaction takes place in terms of reactivity of the halogens. So, we're bubbling chlorine gas, so Cl2, through Br- to get bromine, and then we're going to also form Cl-, so balance that. So Cl2 plus 2 Br- goes to 2 Cl-, 2 Cl- plus Br2. And our chlorine is a gas, our bromine is aqueous, our chloride ions are aqueous, our bromide ions, and our bromine is aqueous. And then we need to explain the reactivity. So chlorine is more reactive than bromine, because reactivity down the group reactivity decreases. And you should know that from GCSE. And then chlorine is used in water treatment. State one benefit and one risk of chlorine in water treatment. So when we put chlorine in water, it forms, well, I'll write out the equation. And then, HClO, not HClO minus, and then HClO goes to ClO minus and H plus. So the ions that it forms, and especially the chlorate 1 ions, ClO minus, chlorate 1, they kill bacteria in the water. So we can just put that it kills bacteria, or that it makes water potable. So that just means drinkable. And then risk of chlorine in water is that you could say that chlorine is toxic, or that it may form chlorinated hydrocarbons. So the chlorine might react with hydrocarbons formed from decaying vegetation. And chlorinated hydrocarbons are carcinogens, so they can cause cancer. Part C, precipitation reactions can be used to distinguish between halide ions. State the reagent needed for these precipitation reactions. So we know from earlier that's AgNO3. How would the appearance of precipitated allow you just to distinguish between chloride, bromide, and iodide ions? So chlorides form a white precipitate, bromide form a cream precipitate, and iodide form a yellow precipitate. And then you can go a step further, not in this question, but you could go a step further in your qualitative testing, and AgCl is soluble in dilute ammonia. Silver bromide is insoluble in dilute, but NH3, but it's soluble in concentrated. And then silver iodide is insoluble even in concentrated ammonia. So that just helps you distinguish between them because they can have quite similar colours. 24A. We've got a 4 marker. Aqueous lead nitrate, PbNO32, and aqueous potassium iodide, Ki, react together. The equation is shown below. So PbNO32 plus 2 Ki, so that's 1 to 2, PbNO32 to Ki, goes to PbI2, so, and 2 KNO3. The student carries out an experiment to determine the enthalpy change of reaction delta RH of this reaction. The student follows the method outlined below. So, this can give us our moles of PbNO3 because we've got a concentration and our volume. Measure out 50 centimeters cubed of Ki, which is in excess, that's important. So we know that our limiting reagent is going to be our PbNO3. Measure the temperature of both solutions. And then add the Ki to the polystyrene cup, stir the mixture and record the maximum temperature. So this is how we can calculate our temperature change. Delta T. Then calculate, so they want us to calculate enthalpy change of reaction in kilojoules per mole for the reaction shown in the equation above. Give your answer to an appropriate number of sig fig. So, in the question, we've got 3 sig fig here, 3 sig fig here, 3 sig fig, 3 sig fig, 3 sig fig. So I see no reason why not to do 3 sig fig again. So we'll make a note of that. And then we need to assume that the density of all solutions and the specific heat capacity is the same as for water. So we're using the equation to find the energy released, QC equals MC delta T. So that's Q equals our mass, which is the sum of our... So when this can be quite a hard style of question for some students because there's multiple different ways to do it. But when we're adding two solutions together, when we're releasing the energy, that's going to heat the entire volume, which is 100 centimeters cubed. And 100 centimeters cubed is 100 grams because the density of water is 1 gram per centimeter cubed. So if you use your formula, density equals mass over volume, you can work out what that means. But essentially, your mass is your volume, so that's 100 grams, times by C, which is 4.18, that's the specific heat capacity of water, times by delta T, which is our change in temperature. So for that we need to do 30 minus 19.5. Straight away, this is where we need to think, right, our temperature is increased, it's become greater. So it must be an exothermic reaction because exothermic reactions release energy to their surroundings. That means that we must have a negative enthalpy change of reaction. So we'll go ahead and put our negative sign there straight away. So, and then we need our temperature change 10.5 degrees. And then we put that into the calculator and that gives us a value of 4,389 joules. We divide that by 1,000 straight away because they want it in kilojoules per mole. So divide that by 1,000 and you get 4.389 kilojoules. And then we want to we want to find our moles. And we want to find the moles of our limiting reagent because that's the only one we've really worried about. So to find that, we know that that's PbNO3 because as we said earlier, they've told us that Ki is in excess. So our moles of PbNO32 are 50 centimeters cubed over 1,000 times by 1.5 mole per dm cubed, which is 0.075 moles. And then we can use that to find our enthalpy change reaction by dividing our kilojoules, our energy released, by our moles to get our enthalpy change value in kilojoules per mole. So always pay attention to your units that you need to use, which is 58.52 kilojoules per mole. But as we said earlier, we need to give it in 3 significant figures. So that's 58.5. Write an ionic equation for the reaction that the student carried out. So, our ionic equation is going to be, well, let's see what ions we've got, and then we can work it out from that. So Pb2 plus, I'll write it up here, and then because the full equation is up here, Pb2 plus 2NO3 minus plus 2K plus 2I minus goes to Pb2 plus 2I minus plus 2K plus 2K plus and 2NO3 minus. So then we just cancel out all the ions which are, sorry, this is wrong, you need to, it's just Pb2 because you've removed the ions. So then remove K plus, remove NO3 minus, and you get your ionic equation. Then consider that we need to include state symbols. We need to read through our questions fully, and then that gives us aqueous goes to PbI2 solid. And then 50 centimeters cubed of Ki used in the experiment contains 10% more Ki than is needed to react with 50 centimeters cubed of 1.5 mole per dm cubed PbNO3. Calculate the concentration in mole per dm cubed of Ki that the student used. Okay, so we need to find we know our moles of PbNO32 because that is 0.075 moles, and our equation shows a 1:2 ratio. So we multiply that by 2 to find the moles of Ki that are needed to react. So that's 0.075 times 2, which is 0.15 moles, and then we need to find our concentration. Concentration is going to be well, 10% more. So we got 10% more than we need, which is 0.15 moles. So find our concentration first, which is 0.15 moles over 50 divided by 1,000 to convert to dm cubed. That's 0.05, which gives us 3 mole per dm cubed. Then times that by 1.1 to increase it by 10%. So that's 3 times 1.1 is 3.3 mole per dm cubed. (25A). So we got a long answer question on equilibrium. Quite a nice question, I think. Sulfur trioxide is used for the industrial manufacture of sulfuric acid, so H2SO4. SO3 is produced by reacting sulfur dioxide, SO2, and oxygen as shown below in equilibrium 25.1. So in equilibrium we've got 2 moles of SO2 reacting with 1 mole of oxygen, forming 2 moles of SO3, and it's an exothermic reaction because we have a negative enthalpy change. So Le Chatelier's principle can be used to predict how different conditions affect the equilibrium position. Using Le Chatelier's principle, show that a low temperature and a high pressure should be used. Show that a low temperature and high pressure should be used to obtain a maximum equilibrium yield of SO3. So our desired product. Explain why the actual conditions used in industry may be different from the conditions needed for a maximum equilibrium yield. So a high temperature is needed because it's a low temperature is needed because the forward reaction is exothermic / you could also say that the enthalpy change is negative, and then high pressure because the right hand side has fewer gaseous moles it's important you say gaseous moles than the left. So temperature means the equilibrium shifts right in the exothermic direction, and pressure means that equilibrium shifts right in the direction of the fewest gaseous molecules. And then why in industry is it a higher temperature and a lower pressure. So industry, low temperature will give a slow rate of reaction because the kinetic energy won't be high enough to achieve the activation energy. Might not be high enough to achieve the activation energy. And then you can also say high pressure is expensive to maintain or is a safety risk because it could be explosive. Then we've got a floor marker on Kc. Under certain conditions, Kc for equilibrium 25.1 is 0.16 dm cubed per mole to the minus 1. The equilibrium mixture under these conditions has the following concentrations of SO2 and O2. So, using the value of Kc, explain whether the equilibrium position will be towards the right or towards the left under these conditions. Calculate the concentration of SO3 in the equilibrium mixture. So, our Kc expression, we'll write that first. That is, let's use our equation. So we've got 2 moles of SO3, 2 moles of SO2, and 1 mole of O2. So our products on top, squared, and then SO2 squared and O2. Reactants on the bottom. And then we can use the values that we've been given to calculate the moles of the concentration of SO3. So we need to rearrange. So Kc times SO2 squared times O2 is equal to SO3 squared. So then we do our Kc value, which is 0.16 times 2 times 1.2, which gives us 0.768 mole per dm cubed. And then, sorry, no, you need to do 2 squared, so that's not right. So 0.16 times 2 squared times, this is where you got to be so careful because see I missed that there. So 0.768, and then and then then we need to say that Kc is less than 1. That means that the equilibrium less than 1. So equilibrium is shifted to the left. But then we need to, sorry, I forgot to square root, because it's SO3 squared, so SO3 concentration is going to be 0.768, which is 0.876 mole per dm cubed. So always double check your square roots, your squares. And then 26. Compound B, shown below, can be used to synthesize organic compounds with different functional groups. So we've got an alkene. Compound B is a member of a homologous series. Name the homologous series and state its general formula. So it's the alkene homologous series, and the general formula of alkenes we know is CnH2n. So if we had, for example, here we have 1, 2, 3, 4 carbon atoms, so then we must have 8 hydrogens. Let's just check that. 1, 2, 3, 4, 5, 6, 7, 8. Yeah. So that's CnH2n. What reagents and conditions are needed to convert compound B into a saturated hydrocarbon? So we're going to need to do hydrogenation using hydrogen in the presence of a nickel catalyst. Some reactions involving compound B are shown in the flowchart below. Complete the flowchart showing the structures of organic compounds C and D. So it can be heated with concentrated sulfuric acid to make an alkene. So then it must be an alcohol because it must be dehydrated, or elimination must occur to form that alkene. So we need to learn our synthetic routes, and then we can see here that it's not reacting with acidified potassium dichromate even under reflux. That means that it must be a tertiary alcohol, because tertiary alcohols resist all forms of oxidation. Therefore, it needs to have this structure. So you might have assumed that that the alcohol group could have been on this on this carbon, but it can't be because that wouldn't be a tertiary alcohol. So always check every single bit of information they give you. And then compound D is a repeat unit of a polymer formed from compound B, so it's going to be an addition polymer, and we draw it like ethene. So draw a single bond, because this bond here is going to break and add across to form our polymer links, which are going to draw them nice and long, and then our groups attached to these carbons, and then like that. Part C. What is the empirical formula of compound F? So let's see what the molecular formula is. So we've got 1, 2, 3, 4 carbons, so that's C4. Then we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 hydrogens and 2 oxygens. So how can we make that simple? Well, you obviously just divide by 2, so that's C2H5O. It's because the empirical formula, as we know from GCSE, is the simplest whole number ratio of atoms in a compound. We're almost at the end now. A student plans a two-stage synthesis for preparing compound F from compound B. The synthesis first prepares compound E as shown in the flowchart. Draw the structure of compound E in the box and state the reagents for each stage on the dotted lines. So we've got another synthesis routes, a two-stage synthesis, which is the most they ask you at AS. So we need to consider what we're starting with, which is compound B, and what we're finishing with. So we're starting with an alkene, and we're finishing with a dialcohol. We've got the same number of carbons, 1, 2, 3, yeah, 4. So we need to consider how we're going to get there. And what our intermediate is going to be. So you couldn't just use steam to do electrophilic addition, because you're going to get a hydrogen on one of these carbons and then you're not going to be able to do anything with it. So we need to somehow get a dialcohol from that compound. So you could do electrophilic addition with bromine or any halogen, so you could do chlorine as well. And that's going to add it across the double bond, form this compound. And then to get from our dichloroalkane to our dialcohol, we need to then use excess NaOH, which will form OH- and do nucleophilic substitution, replacing the chlorine groups and forming a dialcohol. So that's the AS paper for breadth in chemistry 2016. You can see I've finished it in under the time limit. The time limit is 1.5 hours, and I've managed to finish it in 1 hour and 22 minutes, despite explaining it to you guys. So you have lots of time in your chemistry exams. Maybe not paper 3 as much, but still you have lots of time to be careful about your answers and to read the questions fully. So yeah, there's some good tips for you. Be sure to check out my other videos. I've got lots of exam question walkthroughs and topic videos, topic revision videos. Also check out my website. I've got a lot of resources available. We're going to be coming out with some free resources soon as well. I've got I'm thinking about making a planner, and yeah, you can purchase flashcards and notes on my website. So be sure to check that out. The link will be in the description. Thanks for watching, and yeah, make sure to check out my other videos.